There is a discomfort in standing before something too large to see, not too distant to observe, not too small to detect, simply too vast for the mind to hold as a single thought. We are creatures built to navigate rooms, forests, and coastlines. Our intuitions about space were shaped by the land beneath our feet, by the sky we could reach with a pointing finger. What lies beyond that sky was, for most of human history, a matter of myth and mathematics. But mathematics eventually told us something that myth never prepared us for. Between the galaxies, between the enormous luminous structures we can see, there is something else entirely. Not a faint scattering of stars, not a thin mist of gas and dust, something closer to true, unyielding absence. Regions so vast that entire galaxy clusters, if placed inside them, would be lost without a trace. We call them cosmic voids, and the word void, however ancient, barely does them justice. They are not simply empty. They are wrong in the way that a missing chapter in a story is wrong. An absence that implies something was supposed to be there. To understand why they exist, what they mean, and why their scale defies everything intuition offers, we must begin with something closer to home, the very way the human mind encounters space itself. Chapter 1. The Question at the Edge of Sight. When astronomers first began counting galaxies in earnest, they were engaged in what seemed like a straightforward act of inventory. The tools were improving, the telescopes were larger, the photographic plates were more sensitive, and so, systematically, patiently, they pointed their instruments at the sky and recorded what was there. What they were not looking for was what was not there. This is worth sitting with for a moment. The idea that absence requires a particular kind of attention. We are instinctively drawn to objects, to presences, to the things that announce themselves through light or mass or motion. A galaxy is visible. It radiates. It occupies a position in space that can be catalogued, measured, assigned coordinates. Emptiness, by contrast, makes no such announcement. It offers nothing to the instrument and nothing to the eye. And for most of the 20th century, the emptiness between galaxies was treated more or less the way we treat silence in a conversation, as a neutral background, a gap between the meaningful parts. The assumption was reasonable. The universe, after all, had expanded from a state of extraordinary uniformity. The earliest light we can detect, the cosmic microwave background, a faint thermal glow left over from roughly 400,000 years after the Big Bang, is almost perfectly smooth. The temperature variations across it are so slight that early instruments could not detect them at all. From that near-perfect smoothness, the reasoning went, structure had grown gradually. Gravity slowly coaxing matter together over billions of years, and if structure grew gradually, it should be, more or less, spread evenly across the sky. There might be regions of higher and lower density, naturally, but the overall texture of the universe, at large enough scales, should be something like uniform. The sky, it turned out, had different ideas. As galaxy surveys grew more sophisticated through the latter half of the 20th century, as astronomers began assembling not just flat maps of where galaxies appeared on the sky, but true three-dimensional maps that incorporated distance, a different picture began to emerge. Not a uniform scatter, not a gentle gradient of denser and less dense regions. Something altogether more structured, more intricate, and in certain respects, far more extreme than anyone had anticipated. Galaxies were not spread evenly through space. They were gathered into long, thin filaments. They congregated at the intersections of those filaments into enormous clusters. They lay along vast, flat sheets that stretched across hundreds of millions of light years. And between those filaments, between those sheets and clusters, there were regions where almost nothing was. Not sparse, not thin, Genuinely, profoundly empty. The word that eventually settled into the scientific literature was straightforward enough: voids. Regions of the universe significantly underdense compared to the cosmic average. In many cases, so underdense that a volume which should, statistically, contain thousands of galaxies contains only dozens or fewer. In the most extreme cases, a region hundreds of millions of light-years across may contain almost no bright galaxies at all. The scale here is important to hold in mind, even if it resists full comprehension. A single light-year is roughly 9.5 trillion kilometers. The distance light, moving at 300,000 kilometers per second, covers in an entire year. A single galaxy like our own Milky Way spans around 100,000 light-years. The distances between neighboring galaxies are measured in millions of light-years, and a cosmic void, a single void, one of thousands identified in modern surveys, may span hundreds of millions of light-years in every direction. These are not gaps between objects. They are absences on a scale that dwarfs everything we ordinarily mean by the word large. And yet the discovery of voids was, in a peculiar way, almost accidental. The astronomers making those early three-dimensional maps were not hunting for emptiness. They were hunting for structure, for clusters, for filaments, for the patterns of matter distribution that would illuminate how the universe evolved from its smooth beginnings into its complex present. The voids appeared in the negative space of those maps, the way the background of a painting can sometimes resolve into a second image if you look long enough. They were not the point. They were what was left when the point had been removed. This is what makes cosmic voids so intellectually unusual. They are not things in themselves, or rather, they are not things in the way a galaxy is a thing, bounded and luminous and countable. They are defined entirely by what they lack. To study a void is to study an absence, which requires a prior understanding of what ought to be present. It demands a baseline, a picture of how the universe should look if everything were arranged according to average expectations, against which the deviation of a void can be measured. The void exists as a concept only in relation to the structure surrounding it. And yet, and this is the first of many paradoxes this story will encounter, voids are not marginal features of the universe. They are not the exception to the rule of structure. By volume, they dominate. The filaments and walls and clusters that trace the cosmic web occupy a relatively thin architecture, a skeleton of matter. The flesh of the universe, the vast majority of its volume, is void. When astronomers look at maps of large-scale structure, those sweeping visualizations of the cosmic web that resemble uncannily the neural networks of a brain, what they are mostly looking at is the boundary between the matter and the emptiness. The emptiness itself is the larger part of the picture. This inversion, the idea that the universe is, in volume, mostly nothing, sits uncomfortably against the way we tend to think about creation and structure. We imagine a cosmos built outward from matter, filled in progressively with light and complexity. The voids suggest a different reading. That structure was carved out of near uniformity not by filling, but by evacuation. That the emptiness is not what remains after structure forms, but is itself a kind of structure, the inevitable counterpart to every filament and cluster, growing as matter flows away from it, deepening as the universe ages. Why should this feel wrong? Perhaps because emptiness, in our ordinary experience, is always local and temporary, the space between furniture, the silence between words. We do not have an intuition for emptiness that persists, that grows, that spans distances so vast that light itself takes hundreds of millions of years to cross them. The universe does. There is a moment in the history of any scientific field when the map being drawn begins to contradict the map that was expected. It is rarely a single observation that causes this. It is more often an accumulation, a slow build of data that resists the available explanations until the weight of it becomes undeniable. The discovery of cosmic voids was that kind of moment for cosmology. Not a single dramatic revelation, but a gradual recognition that the universe, at its largest scales, was organized in a way that existing theory had not fully predicted, and existing intuition could not easily absorb. The question that emerged from those early surveys was deceptively simple. Why are the voids there at all? On the surface, this might seem like asking why anything is anywhere. A question so broad it dissolves into philosophy before it can become science. But it is in fact a precise physical question with a precise physical answer that cosmologists are still in the process of fully working out. The universe began in a state of near uniformity. Quantum fluctuations in the earliest fractions of a second after the Big Bang introduced tiny variations in density, regions infinitesimally more or less dense than their surroundings. Over the billions of years that followed, gravity amplified those variations. Regions slightly denser than average attracted more matter, grew denser still, and eventually became the filaments and clusters visible in today's cosmic web. Regions slightly less dense than average lost matter to their surroundings, became less dense still, and eventually became the voids. This process, the gravitational amplification of initial fluctuations, is called cosmic structure formation, and it is among the most thoroughly studied phenomena in modern astrophysics. The broad outlines of it are well established. The details, particularly at the scales relevant to the largest voids, continue to generate active research and, occasionally, genuine puzzlement. Because the voids that observation reveals are not always precisely the voids that simulation predicts. This is a subtle but important distinction. The standard model of cosmology, built around cold dark matter, dark energy, and the geometry of spacetime described by general relativity, produces simulated universes that contain voids. Run the equations forward from the observed initial conditions, and emptiness emerges naturally. But the size distribution of those simulated voids, their precise degree of underdensity, their relationship to the surrounding structure, these do not always match what telescopes find. In some regions of the sky, the observed voids are larger, or emptier, or more sharply bounded than the simulations suggest they should be. The discrepancies are not always large enough to overturn the model, but they are persistent enough to suggest that the model may be incomplete, or that the physics operating within and around voids involves something not yet fully captured by the standard framework. Dark energy is the most frequently invoked candidate for what that something might be. The accelerating expansion of the universe, driven by whatever dark energy is, whether a cosmological constant or a more dynamic field, affects voids differently than it affects denser regions. Inside a void, where matter is sparse and gravitational attraction is weak, dark energy's expansive influence is relatively less opposed. Voids, in this sense, are the regions of the universe where dark energy has the most room to express itself, where its signature should be most legible. Studying the growth rate of voids over cosmic time, how quickly they expand, how their profiles evolve, offers one of the most sensitive available tests of dark energy's properties. The void is not merely an absence, it is an instrument. This reframing, from void as gap to void as probe, is one of the quieter revolutions in observational cosmology over the past 2 decades. When astronomers began to take voids seriously as scientific objects in their own right, rather than simply as the space between more interesting things, the field that emerged around them turned out to be remarkably rich. Void statistics. The number of voids of a given size in a given volume of the universe carry information about the universe's geometry, its expansion history, and the nature of the forces shaping its large-scale structure. A careful census of voids, it turns out, can tell you things about the cosmos that a census of galaxies alone cannot. And there is something fitting about that. The universe keeps its information distributed across both what is present and what is absent. To read only the matter is to read only half the text. Yet even as the science of voids has matured, the original sense of strangeness has not entirely dissolved. That strangeness lives in the numbers. It lives in the attempt to hold in mind what a region 300 million light-years across and nearly empty of galaxies actually represents in physical terms. Not as a mathematical abstraction, but as a place, a volume of actual space sitting out there in the observable universe right now, expanding quietly as the cosmos ages around it. Most of the universe's volume consists of regions like this. Not the glittering filaments, not the dense clusters, not the galaxy groups and walls that we photograph and catalog and name. The majority of what exists, spatially speaking, is void. This is not a melancholy observation. It is a structural one. And structure, in science, is always meaningful, always pointing somewhere, always raising the next question. The voids point toward the physics of their own formation, toward dark matter and dark energy, toward the initial conditions of the universe, toward the way gravity and expansion have been in dialogue across the entirety of cosmic time. They point toward the unsolved problems that make cosmology, at this moment in history, one of the most alive fields in all of science. They also point inward in a way that will become increasingly relevant as this story continues, because the emptiness of the cosmos is not something that exists only at a safe remove, out beyond the range of our instruments and our imagination. The question of where we sit within the large-scale structure of the universe, whether we are embedded in a wall, a filament, a cluster, or something else entirely, turns out to have a surprising and disquieting answer. One that changes the meaning of the voids from a distant curiosity into something considerably more personal. But that belongs to a later part of the journey. For now, it is enough to sit with the question as it first presented itself. Why, in a universe that began so smoothly, did such profound emptiness learn to exist? Chapter 2. A mind not built for this. The human brain is, among other things, a remarkable spatial machine. From the earliest weeks of life, it begins constructing a model of the world around it, assembling distance, depth, and dimension from the raw data of two eyes set slightly apart in a skull, from the tension of muscles as they reach and grasp, from the way sound arrives at each ear at fractionally different moments. By adulthood, this model is so refined, so automatic, that we do not experience it as a model at all. We experience it as reality. The space around us feels given, self-evident, simply there. This is, in evolutionary terms, an extraordinary achievement. The ability to judge distance accurately, to know whether a branch will hold weight, whether a predator is close enough to warrant flight, whether a thrown object will reach its target, conferred enormous advantages across the long span of human prehistory. Our spatial intuition was built by survival, calibrated over hundreds of thousands of years against the scale of the world we actually inhabited. Landscapes, valleys, the distance between one water source and the next, the height of a tree, the width of a river. Nothing in that history prepared us for the scale of a cosmic void. This is not a failure of intelligence. It is a failure of range. The cognitive tools we use to navigate space were never designed to operate at cosmological scales, in the same way that an instrument calibrated to measure millimeters is not defective when it fails to measure the diameter of the Earth. The instrument is simply operating outside its designed domain. And cosmological scales are not merely larger than human scales in a quantitative sense. They are larger in a way that constitutes a qualitative rupture. There is no smooth continuum of experience connecting the size of a room to the size of a galaxy supercluster. The numbers increase, but the intuition does not follow. Consider what the mind actually does when confronted with a very large number. When we hear that a particular void spans 300 million light-years, we register that this is large, very large. But the cognitive response is essentially the same as the one triggered by any number that exceeds our immediate grasp. Psychologists who study numerical cognition have found that human beings are genuinely skilled at distinguishing quantities up to roughly 4 or 5 items without counting. Beyond that, estimation takes over, and at very large magnitudes, the brain effectively compresses the scale, treating a million and a billion as both simply meaning a great many. The emotional and spatial weight we attach to 300 million light-years is not meaningfully different from the weight we attach to 300,000 or 3,000. The number has lost its grip on lived experience. This compression has consequences for how we engage with the universe. It means that the true strangeness of cosmic voids, the genuinely alien quality of their scale, is very difficult to feel, even after it has been intellectually understood. Knowing that the Boötes void could contain dozens of Milky Way-sized galaxies end to end, and yet contains almost none, does not produce in most people the vertigo it logically should. The knowledge sits correctly in the mind without disturbing the felt sense of things. And this gap between understanding and feeling is not a personal shortcoming. It is a structural feature of the kind of minds we are. The history of astronomy is, in part, a history of the universe repeatedly exceeding its observers' expectations in exactly this direction, turning out to be older, larger, emptier, and stranger than the picture current at any given moment. When Copernicus removed the Earth from the center of the solar system, the psychological adjustment required was not merely philosophical. It demanded a renegotiation of the felt relationship between the observer and the observed. When the distance to the nearest stars was first reliably measured in the 19th century, using the parallax method, which detects the tiny shift in a star's apparent position as the Earth moves around the Sun, the numbers were so far beyond ordinary experience that many astronomers initially doubted them. When Edwin Hubble demonstrated in the 1920s that the spiral nebulae scattered across the sky were not clouds of gas within the Milky Way, but entire galaxies, each containing hundreds of billions of stars at distances of millions of light-years, the revision of scale required was so extreme that it has never fully settled into common intuition, even a century later. Each of these expansions in the known scale of the universe was accompanied by the same basic cognitive challenge. The human mind had to extend its model of space into a domain where its ordinary tools no longer applied. And each time it managed, not by feeling its way there, but by developing new representational strategies, new mathematics, new visualizations, new conceptual frameworks that could carry meaning across a gap that perception alone could not bridge. This is the deeper story behind the discovery of cosmic voids. The voids were not simply found by pointing telescopes in the right direction. They were found because astronomers developed the tools, both technological and conceptual, necessary to represent the three-dimensional distribution of matter at scales the unaided mind cannot hold. The redshift survey, which uses the stretching of light as it travels through expanding space to assign distances to galaxies, is one such tool. It converts what the eye sees as a flat scattering of points into a volume, a three-dimensional structure with depth and texture. Without that conversion, the voids remain invisible, not because the light isn't reaching the telescope, but because the data cannot yet be assembled into a form the mind can parse. What those assembled maps revealed, when they finally came, was not just the existence of voids, but the existence of a level of structure in the universe that theory had gestured toward, but observation had never before confirmed so dramatically. The universe was not a gentle gradient, it was a web, intricate, hierarchical, and punctuated by absences so large they seemed, at first encounter, almost impossible to credit. The astronomers who made those early maps were not working at the edge of their instruments alone. They were working at the edge of their intuitions, constructing a picture of the universe that their own minds were not naturally equipped to inhabit. There is a concept in cognitive science sometimes called the model of the world, the internal representation the brain maintains of its environment, updated continuously through sensory experience. This model is not a passive recording. It is an active construction, constantly predicting what comes next, filling in gaps, smoothing over inconsistencies. When you walk through a familiar room in darkness, you do not experience blindness so much as a confident reliance on the model already built from previous visits. The room exists in your mind before your foot finds the floor. This predictive quality is enormously useful. It is also, at cosmological scales, a source of persistent error. The brain fills gaps with what it expects. In spatial reasoning, what it expects is governed by the scales it has experienced. When confronted with an unfamiliar environment, a vast cave, an open ocean, a mountain range seen from above, the mind reaches for the nearest available analogy, the closest thing in memory that approximates the new experience. This is not a flaw. It is the only strategy available to a system that must act continuously and cannot wait for complete information. But it means that the mind's first model of any genuinely novel scale is almost always wrong, calibrated to the familiar rather than the actual. Astronomers are not exempt from this. The history of theoretical cosmology includes numerous examples of models that turned out to have been unconsciously shaped by the scale of what was already known. Early estimates of the size of the Milky Way were too small. Early models of galaxy distribution assumed more uniformity than the data eventually supported. The intuition that the universe, at large enough scales, must be smooth and featureless, a principle formalized as the cosmological principle. The assumption of homogeneity and isotropy was not wrong exactly, but it required a significant qualification once the cosmic web became visible. The universe is smooth only at the very largest scales. Below those scales, the structure is anything but. What this means practically is that every expansion of cosmological knowledge has required a deliberate act of conceptual reconstruction, a willingness to let the new data override the inherited model, even when the inherited model felt self-evidently reasonable. This is harder than it sounds. The felt reasonableness of an expectation is not a reliable guide to its accuracy, and the larger the scale under investigation, the larger the gap between what feels right and what the data actually shows. The tools that allow astronomers to bridge this gap are worth examining not just as technical achievements, but as cognitive ones. A redshift survey does not merely measure distances. It creates a new kind of representational space, a volume in which the positions of galaxies can be plotted in 3 dimensions, and in which the texture of large-scale structure becomes visible in a way it cannot be from a flat image of the sky. Looking at a slice through such a survey, a wedge-shaped map showing the distribution of thousands of galaxies across hundreds of millions of light-years, is one of the few experiences in which the human visual system can engage directly with cosmic structure. The voids are immediately apparent, even to an untrained eye. The filaments are visible. The clustering is unmistakable. This is significant because it suggests that the mind's spatial processing, while calibrated for the scale of ordinary experience, can be recruited for larger scales when the data is presented in the right form. The brain that cannot feel the three-dimensionality of a void 300 million light-years across can nonetheless respond to the visual pattern of a map. It can recognize structure. It can detect absence. The cognitive limitation is not absolute. It is a limitation of direct sensory experience, which can be partially compensated for by representation. This is, in miniature, the story of how science extends human cognition beyond its natural range. Not by replacing the mind with something else, but by providing the mind with scaffolding, representations, models, visualizations, mathematical formalisms that carry meaning across scales where perception cannot go unassisted. The void that the eye cannot see, the number that the mind cannot hold, the scale that intuition cannot span. All of these become tractable, if not fully intuitive, when the right representational tools are in place. The development of those tools did not happen instantaneously. The three-dimensional mapping of large-scale structure required not only the technology to collect spectroscopic data at scale, measuring the redshifts of thousands, then tens of thousands, then millions of galaxies, but the computational infrastructure to process and visualize that data in meaningful ways. The first clear pictures of the cosmic web emerged only when computing power had advanced sufficiently to handle the volume of information involved. In this sense, the discovery of voids was as much a story about the evolution of scientific instrumentation and computation as it was about the universe itself. And woven through all of it was the persistent challenge of communication, of conveying to other minds, including non-specialist ones, what the data actually showed. This challenge has not been fully solved. The images produced by modern cosmological surveys are among the most visually striking in all of science, but they carry a kind of deceptive familiarity. The cosmic web, rendered as a luminous network against a dark background, looks comprehensible, almost biological in its structure. The voids appear as dark regions, which the eye reads easily as empty. But the scale at which this image exists, and the physical processes that produced it, remain largely beyond felt understanding, even for those who study it professionally. What remains, when the tools are in place and the maps have been made, is a kind of disciplined humility, and acknowledgement that the universe does not owe its structure to human intuition, and that the discomfort of encountering something genuinely beyond ordinary experience is not a problem to be solved, but a condition to be inhabited. The voids are there, whether or not we can fully feel their scale. The cosmic web is structured as it is, regardless of whether the structure sits comfortably within our inherited model of space. Learning to think at these scales does not mean learning to feel them in the way we feel the distance across a room. It means learning to hold the knowledge steadily without the false comfort of analogy, and to let the strangeness remain strange, while still, carefully, asking what it means. That asking is where the science lives, and it begins necessarily with the physics of what the universe is actually made of, and why that composition should produce emptiness at all. Chapter 3. What fills space and what does not? If you were to take the entire observable universe, everything within the roughly 46 billion light-year radius that light has had time to reach us from since the Big Bang, and dissolve it into its constituent parts, the inventory would be, in certain respects, deeply counterintuitive. The stars, the galaxies, the gas clouds and dust lanes and planetary systems that make up everything we have ever directly observed, all of that ordinary matter. Everything that emits or reflects or absorbs light accounts for approximately 5% of the total energy content of the universe. 5%. The remainder is divided between two components that neither emit nor reflect light, that have never been directly detected in a laboratory. and whose fundamental nature remains among the deepest open questions in all of physics. Roughly 27% of the universe's energy content is dark matter, matter that interacts gravitationally, that has mass in the conventional sense, but that does not participate in electromagnetic interactions. It does not shine. It does not absorb. It does not scatter light. Its presence is inferred entirely from its gravitational effects. The way galaxies rotate faster at their edges than the visible matter alone could explain. The way light bends around galaxy clusters more strongly than their visible mass would produce. The way large-scale structure itself could not have formed as quickly as it did without an additional gravitational scaffold invisible to our instruments. The remaining 68% is stranger still. Dark energy, a term that encompasses our uncertainty as much as it describes a substance, is the component responsible for the accelerating expansion of the universe. Unlike matter, which gravity draws together, dark energy appears to act in the opposite direction. It is associated with the expansion of space itself, and as the universe grows, its influence does not dilute but remains constant, or possibly grows. The precise nature of dark energy, whether it is a fixed property of space-time, a dynamic field that evolves over time, or something else entirely, is not known. What is known is that it dominates. In the current epoch of cosmic history, dark energy is the largest single component of the universe's energy budget, and its influence on the large-scale structure of the cosmos is profound. These three components, ordinary matter, dark energy, do not occupy space in the same way or behave according to the same rules. Understanding how they interact and how their interaction produces both the structures we observe and the voids between them is the foundation on which any serious account of cosmic voids must be built. Begin with gravity, which is the organizing force of the universe at large scales. Gravity is attractive. Given time, it draws matter together, first into clouds, then into the first stars, then into galaxies, then into the galaxy clusters and filaments that make up the cosmic web. This process of gravitational collapse, operating over billions of years, is responsible for all the visible structure in the universe. But gravity does not work in isolation. It works against a background of cosmic expansion, the ongoing stretching of space itself that began at the Big Bang and has continued ever since. In the early universe, these two forces, gravity pulling matter together, expansion pulling space apart, were in a particular balance that determined how quickly structure could grow. The initial density fluctuations seeded by quantum processes in the first fractions of a second after the Big Bang were small, but they were sufficient. Regions very slightly denser than average began to collapse under their own gravity, pulling in surrounding matter, growing denser still. Regions very slightly less dense than average began to lose matter to their surroundings, growing emptier still. This process, amplified over billions of years, produced the cosmic web, and produced, as its necessary counterpart, the voids. The key word here is necessary. Voids are not accidents. They are not the residue of some process that failed to distribute matter properly. They are the direct and inevitable consequence of the same gravitational dynamics that build galaxy clusters. For every region where matter has concentrated above the cosmic average, there must be a region where matter has been depleted below it. The universe conserves its total content. It cannot build a cluster without emptying the space around it. The void and the filament are not opposites. They are the same process seen from its two ends. This symmetry is worth dwelling on because it reframes the void not as an anomaly, but as a fundamental feature of gravitational structure formation. To ask why voids exist is, in a sense, to ask why galaxy clusters exist. The answer to both questions is the same, because the universe began with small variations in density, and gravity amplified those variations without limit. The richest environments in the universe, the great clusters where thousands of galaxies orbit a common center, are rich precisely because they have drawn matter from the regions around them. Those regions are the voids. Dark matter plays an essential role in this process, and its role is particularly important for understanding what voids actually contain. Because dark matter interacts gravitationally but not electromagnetically, it does not collapse into the dense, compact structures that ordinary matter forms. It does not form stars or planets. Instead, it organizes into a diffuse cosmic scaffolding, halos around galaxies, filaments connecting clusters, and a faint, extended presence that traces the large-scale structure of the universe. Within voids, where the density of ordinary matter is extremely low, dark matter is also present, but in similarly reduced quantities. The voids are underdense in dark matter as well as in ordinary matter. Their underdensity is a property of the total matter distribution, not just of the luminous component. This matters because it means a void is not simply a region where galaxies are absent. It is a region where the underlying gravitational field is genuinely weaker, where the fabric of mass and energy that shapes space-time is thinner, and in that thinness, something else begins to dominate. When matter is sparse, dark energy speaks more clearly. This is not a metaphor. It is a statement about the balance of physical forces operating in a given region of space. In dense environments, gravity is strong. The gravitational attraction between galaxies, between clusters, between the dark matter halos that surround them, dominates the local dynamics. Dark energy's expansive influence is present, but it is, in a meaningful sense, outcompeted. The region holds together against the expansion of space because its own internal gravity is sufficient to resist it. Inside a void, that competition is resolved differently. The matter density is so low that gravity's local pull is greatly reduced. Dark energy, whose density does not diminish as space expands, fills the available volume without meaningful opposition. The result is that voids expand faster than the universe as a whole. They are the regions where the acceleration of cosmic expansion is most purely expressed, where the influence of dark energy on the geometry of space is least obscured by the gravitational noise of matter. A void is, in this precise physical sense, the most dark energy-dominated environment in the observable universe. This has an important observational consequence: the rate at which voids grow over cosmic time, how quickly their boundaries expand outward as matter continues to drain away along filaments, is sensitive to the properties of dark energy. A universe with a stronger dark energy component would produce voids that grow faster and reach larger sizes. A universe where dark energy evolves over time, becoming stronger or weaker as the cosmos ages, would produce a void population whose statistical properties differ in detectable ways from one where dark energy is a fixed constant. By measuring the size distribution of voids at different epochs in cosmic history, looking at voids far away, which we see as they were billions of years ago, and comparing them to voids nearby, astronomers can, in principle, read the history of dark energy's behavior directly from the structure of emptiness. This is one of the reasons voids have moved from the margins of cosmological research toward its center over the past 2 decades. They are not merely interesting features of the large-scale structure. They are sensitive probes of the physics that governs the universe's largest scales. Physics that is, in important respects, still not fully understood. But return for a moment to the question of what a void actually contains. The word emptiness, applied to a cosmic void, requires qualification. These regions are not empty in the absolute sense, not the perfect vacuum of an idealized thought experiment. They contain gas, tenuous and diffuse, the remnants of matter that was never quite dense enough to collapse into stars. They contain radiation, the same faint microwave background that fills all of space. They contain dark matter, spread thin but present, and they contain, occasionally, galaxies. Small ones, typically, dwarf galaxies that formed from the sparse material available within the void and have evolved in profound isolation, without the gravitational interactions and mergers that shape galaxies in denser environments. These void galaxies are among the most unusual objects in the universe. A galaxy that forms and evolves inside a large void does so in conditions radically different from those experienced by a galaxy in a cluster or along a filament. It has fewer neighbors. It accretes gas more slowly. It is not subject to the tidal forces and close encounters that disrupt galactic structure in crowded regions. In some respects, void galaxies are simpler objects than their counterparts in denser environments, less disturbed, less processed, more reflective of the initial conditions from which they formed. Studying them offers a window into galaxy formation that is partially obscured elsewhere by the complexity of environmental interactions. The existence of these galaxies also serves as a reminder that the boundary between a void and its surroundings is not sharp. Voids do not have walls in any literal sense. Their edges are gradients, regions where the density transitions from the extreme underdensity of the void interior to the average density of the surrounding universe, and then to the overdense filaments and walls that bound them. This gradual transition means that the definition of a void is, to some extent, a matter of convention, of the threshold at which an astronomer decides underdensity is sufficient to constitute a distinct region. Different surveys use different criteria, and the resulting void catalogs differ in their details, though their broad features are consistent. What all definitions agree on is the degree of contrast. A typical large void has an interior density that is somewhere between 10 and 30% of the cosmic average, meaning that if you randomly selected a point inside such a void, the matter density at that point would be less than 1/3 of what you would expect at a randomly selected point anywhere in the universe. In the most extreme voids, the contrast is even greater. This is not a subtle statistical underdensity. It is a profound depletion, sustained over volumes so large that the word region begins to feel inadequate. The physics that produces this depletion is the same physics that produces everything else in the cosmic web: gravity, expansion, the interplay between dark matter's scaffolding and ordinary matter's tendency to collapse. Voids are not the product of a different set of rules. They are the product of the same rules applied consistently over the full range of initial density fluctuations, from the highest peaks to the lowest troughs. The universe, in this sense, is entirely self-consistent. Its structure formation produces both the richest and the emptiest environments from the same set of initial conditions, operating through the same fundamental forces. And yet the result, a universe in which the majority of volume is occupied by regions this empty, this dark, this removed from the luminous activity of stars and galaxies, still carries a quality of genuine surprise. Not because the physics is wrong, but because the physics, carried to its conclusion, produces something that exceeds what intuition would have offered as a prediction. The universe, given ordinary matter and dark energy and gravity and time, builds a cosmic web. And in building that web, it builds its own absence, vast, structured, physically meaningful, and waiting to be read. Reading it required not just the right physics, but the right instruments and the right methods for turning the light of distant galaxies into a map of the space between them. Chapter 4. Reading the Invisible. There is a particular challenge embedded in the study of cosmic voids that has no real parallel in other areas of observational science. Most scientific instruments are designed to detect something, a particle, a wavelength, a signal of some kind that announces the presence of what is being sought. The void offers none of this. It is, by definition, a region from which the usual signals are largely absent. To study it, astronomers must work indirectly, inferring the shape and extent of emptiness from the distribution of matter at its edges. The way a sculptor's form is defined not by the clay itself, but by the space the clay surrounds. This indirection is not a limitation to be apologized for. It is, in its own way, a form of precision, a method that extracts meaning from absence with the same rigor that other methods extract meaning from presence. But it requires tools that were not originally designed for this purpose, and techniques that took decades to develop into their current form. The most fundamental of those tools is the redshift survey. Light, as it travels through the universe, is subject to the expansion of space. The farther a galaxy is from us, the faster the space between us and that galaxy is expanding, and the more the light it emits is stretched toward longer, redder wavelengths by the time it arrives at our instruments. This shift in wavelength, the cosmological redshift, is directly related to the distance the light has traveled, and by extension, to the distance of the galaxy that emitted it. By measuring the redshift of a galaxy's light, astronomers can determine with considerable precision how far away that galaxy is. This seems straightforward, but the practical execution at scale required an enormous investment of observational time and technological development. Early redshift surveys in the 1970s and 1980s could measure the distances to hundreds of galaxies. By the 1990s, that number had risen to tens of thousands. The Sloan Digital Sky Survey, which began systematic observations in 2000, eventually compiled spectroscopic redshifts for more than 3 million galaxies, covering roughly 1/3 of the entire sky. Each of those measurements, each redshift, is a coordinate in a three-dimensional map of the universe. Assembled together, they reveal the texture of large-scale structure with a resolution and completeness that earlier astronomers could not have imagined. When those maps are examined, the voids do not need to be identified by any sophisticated algorithm. They are immediately visible as the dark regions, the zones where galaxy positions are absent, where the survey returns nothing across volumes that should, statistically, contain many detectable objects. Their boundaries are the walls and filaments where galaxy density sharply increases. Their interiors are the silences between those boundaries. But identifying a void visually in a map is only the beginning. Characterizing it precisely, measuring its size, its shape, its degree of underdensity, its relationship to the surrounding structure, requires statistical methods that compare the observed galaxy distribution to what would be expected in a uniform universe. The basic tool for this is the two-point correlation function, which measures how the probability of finding a galaxy at a given location depends on the presence of galaxies at other locations. In a perfectly uniform universe, the correlation function would be flat. The presence of a galaxy at one point would tell you nothing about the likelihood of finding one nearby. In the actual universe, it is strongly peaked at small separations, reflecting the tendency of galaxies to cluster. And it carries information about voids through the underdensity it reveals at the relevant scales. More recently, astronomers have developed void-finding algorithms specifically designed to identify and catalog underdense regions in three-dimensional survey data. These algorithms vary in their approach. Some define voids as spherical regions below a density threshold. Others trace the topology of the density field to identify the deepest underdense basins, but all of them produce catalogs of voids with well-defined positions, sizes, and internal density profiles. Those catalogs are the raw material for the statistical analyses that extract cosmological information from void populations. One of the most important properties that can be extracted is the void size function, the distribution of void sizes within a given survey volume. just as the mass function of galaxy clusters tells cosmologists about the amplitude of density fluctuations and the rate of structure growth. The size function of voids carries complementary information about the low-density tail of the distribution. A universe with more power on large scales will produce more large voids. A universe where dark energy is stronger will show voids that are larger and more numerous at late cosmic times. Comparing the observed void size function to theoretical predictions allows cosmologists to constrain the parameters of their models in ways that galaxy clustering statistics alone cannot achieve. This is the underlying logic of void cosmology as a field. Voids are not merely interesting structures to be cataloged. They are statistical probes of the universe's fundamental properties, and their power as probes comes precisely from their emptiness. Because voids contain so little matter, they are less affected by the complex astrophysical processes, star formation, feedback from black holes, gas dynamics, that complicate the interpretation of observations in denser environments. The physics operating inside a void is, in a meaningful sense, cleaner. Gravity and dark energy operating on a nearly uncluttered stage. But redshift surveys, however powerful, have an inherent limitation that shapes everything built upon them. Light travels at a finite speed. The light arriving at our instruments from a galaxy 1 billion light-years away left that galaxy 1 billion years ago. The map produced by a redshift survey is not a snapshot of the universe as it is now. It is a composite of the universe as it was at different moments in the past, with more distant regions representing earlier epochs. This temporal displacement is not a flaw in the method. It is a feature of the physical situation, and cosmologists have developed sophisticated techniques to account for it. The temporal displacement built into every redshift survey has a name in the literature. It is called looking back in time, and it is both a complication and an opportunity. A complication because the universe at redshift 1, as it was roughly 8 billion years ago, was structured differently than the universe today. Voids were smaller then, less evolved, less deeply emptied by the continued drainage of matter along filaments. Comparing voids at different redshifts as if they were equivalent would introduce systematic errors into any cosmological analysis. An opportunity because that same variation across cosmic time is precisely what carries information about how structure has grown and how dark energy has behaved across the history of the universe. Handling this correctly requires what cosmologists call evolutionary modeling, accounting for the expected change in void properties across redshift and comparing the observed evolution to theoretical predictions. If dark energy has been constant throughout cosmic history, as the simplest model, the cosmological constant, assumes, then the growth of voids over time should follow a specific predicted pattern. If dark energy has instead been dynamic, changing in strength as the universe aged, then the growth rate should deviate from that pattern in ways that, with sufficient data, can be detected and measured. The void population, examined across a wide range of redshifts, becomes a kind of fossil record of dark energy's history. Redshift surveys, however, are not the only instrument in the astronomer's toolkit for studying voids. A second method, gravitational lensing, operates on a completely different physical principle and provides a different and complementary kind of information. Light does not travel in perfectly straight lines through the universe. It follows the curvature of space-time, and space-time is curved wherever mass is present. When light from a distant galaxy passes through or near a region containing significant mass, a galaxy cluster, a dark matter halo, its path is bent, and the image of the distant galaxy appears distorted. This distortion, called gravitational lensing, encodes information about the mass distribution along the line of sight between the source and the observer. Voids, by containing less mass than average, produce a characteristic lensing signal. Not the strong distortion associated with clusters, but a subtle, coherent pattern in which background galaxies near the projected position of a void appear very slightly less distorted than average, because the void's underdensity bends light less than a typical line of sight would. This signal, called void lensing, is extremely weak, far too small to detect around any individual void. But when averaged over many thousands of voids identified in a redshift survey, it becomes measurable. The result is a direct measurement of the mass deficit inside voids, including the dark matter component that cannot be observed in any other way. Void lensing measurements confirmed something that theoretical models had predicted, but observation had not previously verified directly. The underdensity of voids extends to the dark matter distribution, not just the galaxy distribution. The voids identified by their galaxy content are genuinely underdense in total matter, not merely regions where galaxy formation has been suppressed for reasons unrelated to the underlying mass distribution. This distinction matters because it validates the use of voids as tracers of the overall density field, the assumption on which all void cosmology rests. A third observational window into voids comes from the cosmic microwave background, the thermal radiation left over from the early universe, now cooled to approximately 2.7 degrees above absolute zero and filling all of space with extraordinary uniformity. The temperature of this radiation is not perfectly constant across the sky. There are small variations at the level of 1 part in 100,000 that reflect the density fluctuations present in the early universe. The same fluctuations that seeded the formation of all large-scale structure. But superimposed on those primordial fluctuations are secondary effects produced as the CMB photons travel through the evolved universe toward our instruments. One of those secondary effects is the integrated Sachs-Wolf effect, which occurs when CMB photons pass through regions where the gravitational potential is changing over time. In the matter-dominated early universe, gravitational potentials were approximately constant, and photons gained and lost equal amounts of energy as they fell into and climbed out of potential wells. But in a universe dominated by dark energy, gravitational potentials decay over time. The wells become shallower, and photons that fall into a potential well and then climb out find the well has changed during their transit, leaving a net imprint on their energy. Voids, as regions of low gravitational potential, produce a characteristic cold imprint on the CMB through this mechanism, a very slight decrease in temperature in the direction of a large void. This signal has been detected statistically by cross-correlating CMB temperature maps with void catalogs derived from galaxy surveys. Its detection constitutes an independent confirmation of dark energy's influence on the evolution of large-scale structure, a consistency check that links the earliest light in the universe to the largest structures in the present one. It is, in the precise sense of the word, elegant. A method that reads the signature of emptiness in the oldest radiation available to observation. What unites all of these methods, redshift surveys, void lensing, the integrated Sachs-Wolf effect, is the interpretive nature of the work. None of them provides a direct image of a void in the way a photograph provides a direct image of a galaxy. Each provides a signal that must be translated, modeled, and compared against theoretical predictions before it yields information about the void's properties. The astronomer studying a void is always working at one or more removes from the object of study, reading the universe through its effects rather than its emissions. This indirection is not unique to void science. Much of modern astrophysics operates this way, but it is particularly pronounced here, because the thing being studied is defined by what it lacks. Every measurement of a void is, at its core, a measurement of deviation from expectation, a count of fewer galaxies than predicted, a lensing signal weaker than average, a cmb temperature slightly cooler than the surrounding sky. The void exists in the data as a consistent pattern of absences, coherent across multiple independent methods. And it is the coherence of those absences that makes the void real as a scientific object. This is, perhaps, the most important methodological lesson that void science offers to the broader practice of cosmology. The universe does not always reveal itself through what it presents. Sometimes it reveals itself through what it withholds. And learning to read that withholding with the same care and precision applied to any other signal is among the more demanding and more rewarding tasks that observational science has set itself. The maps that emerged from this work, patient, indirect, built from millions of measurements and decades of methodological refinement, told a story about the universe that no single observation could have delivered. And that story had a particular moment, a particular set of maps, and a particular community of scientists at which it first became undeniable. Chapter 5. The Map That Changed Everything. In 1977, a pair of astronomers at the Harvard-Smithsonian Center for Astrophysics began a project whose ambitions were, by the standards of the time, considered modest. Mark Davis and John Hutra, working with colleagues, proposed to measure the redshifts of every galaxy in a selected region of the northern sky down to a certain brightness limit, a defined, systematic sample that would allow, for the first time, a genuine three-dimensional map of galaxy distribution across a significant volume of the universe. The technology required was available, barely. The observational time required was substantial. The scientific return, they believed, would justify both. What they could not have fully anticipated was what that return would look like. The project that grew from that initial proposal, the CFA Redshift Survey, named for the Center for Astrophysics where it was conceived and carried out, proceeded in stages across the late 1970s and 1980s. The first slice of data, covering a thin wedge of the sky roughly 6 degrees wide and extending to a redshift corresponding to a distance of several hundred million light-years, was published in 1986. The map it produced was a wedge-shaped diagram, narrow at the vertex where the observer sat and widening outward as distance increased. Within that wedge, each dot represented a galaxy, its position determined by its location on the sky and its distance determined by its redshift. The pattern those dots formed was not what anyone had been fully prepared to see. Galaxies were not scattered randomly. They were not arranged in a gentle gradient from denser to less dense regions. They were organized into a structure, a tracery of linear concentrations, curved chains, and flat sheets surrounding regions where almost no galaxies appeared at all. The map looked, to the scientists who first examined it, less like a sample of a smoothly evolving universe, and more like the cross-section of something with internal architecture, with walls and rooms, with a geometry that implied large-scale order of a kind that existing models had not predicted in such stark terms. Margaret Geller and John Hutra, who led the extended CFA survey through the late 1980s, described what they saw in the data with a word that has since become iconic in the literature of cosmology: the Great Wall. A sheet of galaxies stretching across the full extent of the survey, hundreds of millions of light-years long and tens of millions of light-years thick, bounding a void on one side and tracing the edge of a filament on the other. It was the largest coherent structure that had ever been identified in the observable universe at that point, and its existence implied that the universe was organized at scales far larger than the models of the time had comfortably accommodated. The CFA maps did something that data rarely achieves so cleanly. They made the abstract visible. The cosmic web, a concept that theorists had gestured toward, but that observation had not confirmed with anything approaching this clarity, was suddenly a picture that could be examined, discussed, and pointed at. The voids in particular were striking. In the wedge diagrams, they appeared as blank regions, large, roundish, strikingly empty compared to their surroundings. Not the kind of emptiness produced by a survey that had missed some galaxies, but the kind produced by a genuine absence in the underlying distribution. One of those blank regions would, within a few years, acquire a name and a significance that extended well beyond the CFA survey itself. The Bootes void had technically been identified before the CFA maps made large-scale structure visible at this resolution. In 1981, Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, conducting an independent survey of galaxy distribution in selected regions of the sky, found something unexpected in the direction of the constellation Bootes. A region of the survey that should, on the basis of the surrounding galaxy density, have contained roughly 100 galaxies, contained instead approximately 5. The volume of space they had sampled was not small. Their survey covered a region extending to several 100 million light-years, and within the portion that later analysis would identify as the void, the galaxy count was close to 0. When Kirshner and his colleagues published their results, they did so with notable scientific restraint. The paper described an apparent underdensity and noted that its extent, if confirmed, would be difficult to reconcile with standard models of structure formation. The void, if real, was larger than theory had anticipated, a region roughly 300 million light-years across, extending through 3 dimensions rather than merely appearing as a gap in a projected sky map. This 3-dimensional extent was what made it genuinely anomalous. A gap in a projected map might be explained in various ways: by the survey geometry, by selection effects, by the particular slice of sky being examined. A gap that persisted across the full depth of the survey, in 3 dimensions, was harder to dismiss. The astronomical community's initial response was cautious. Large voids had been discussed theoretically, but finding one of this scale in a relatively small survey raised questions about whether it was genuinely representative of the universe or simply the result of sampling a particularly unusual region. Additional surveys were needed to confirm the extent of the void and to determine whether it was exceptional or part of a broader pattern of large-scale structure. Those additional surveys, as the 1980s progressed, confirmed both things simultaneously. The Bootes void was real. Subsequent observations found it to be approximately as large and as empty as Kirshner's team had claimed. And it was not entirely unique. Other large voids were identified as the surveys expanded, though none initially as striking in its combination of size and emptiness. What the accumulating data showed was that the universe contained voids across a wide range of scales, from relatively modest underdensities, a few tens of millions of light-years across, to genuinely vast structures like Bootes that challenged the predictions of contemporary models. The challenge was not merely observational, it was theoretical. The existence of a void as large as Bootes required an explanation, a physical account of how, starting from the nearly smooth initial conditions of the early universe, gravity and expansion had managed to produce an underdense region of that scale within the time available. The models of structure formation current in the early 1980s struggled to produce voids of comparable size naturally. The theoretical difficulty posed by large voids was not simply a matter of scale, it was a matter of time. The universe, at the moment those early surveys were being conducted, was understood to be somewhere between 10 and 20 billion years old, an estimate that has since been refined to approximately 13.8 billion years. Within that span, gravity had to work from the nearly smooth initial conditions revealed by the cosmic microwave background, density variations of roughly 1 part in 100,000, and produce, through the slow amplification of those variations, the structures visible in the redshift surveys. Filaments, walls, clusters, All of these required time to grow, but they grew in regions of positive density contrast, where gravity was actively pulling matter together. Voids grow differently. They are not pulled into existence, but evacuated. Matter drains out of them along the gravitational gradient toward denser surrounding regions, leaving the interior progressively emptier over time. This process is, in certain respects, slower than the collapse of overdense regions. A region that is only slightly underdense to begin with takes a very long time to become profoundly empty. And a void as large as Bootes, with the degree of underdensity it appeared to possess, required either a very large initial fluctuation, rare given the smoothness of the early universe, or a very long time to develop, or some combination of the two. The models of the early 1980s, built primarily around ordinary matter and without the full incorporation of dark matter's role in accelerating structure formation, found the Bootes void uncomfortably large. It sat at the edge of what could plausibly be produced within the age of the universe under those assumptions. When dark matter was more fully integrated into the standard model of structure formation, when the cold dark matter framework was established and its predictions for large-scale structure were worked out in detail, the situation improved somewhat. Cold dark matter models could produce large voids, and the Bootes void, while still on the large end of the expected distribution, was no longer entirely outside the range of theoretical prediction. But it remained a useful provocation. It reminded cosmologists that the structures they were finding in surveys were not guaranteed to be comfortably accommodated by whatever model was current. The universe had a habit of producing things slightly larger, slightly emptier, or slightly more extreme than the models suggested it should. The Bootes void was an early instance of that habit, and it would not be the last. What the surveys of the 1980s and 1990s established, beyond any individual structure, was a new picture of the universe at large scales, one that has not been revised in its essential character since, though it has been refined enormously in its detail. The universe is not smooth at scales below several hundred million light-years. It is organized into a web, a network of dark matter filaments traced by galaxies, connecting clusters at their nodes, with vast voids occupying the space between. This web is hierarchical. The largest filaments are built from smaller ones. The largest voids contain smaller subvoids, and the whole structure reflects the statistical properties of the initial density field amplified over billions of years by gravity. The CFA survey and its successors did not merely confirm this picture, they created it. Before those maps, the cosmic web was a theoretical possibility, discussed in the context of specific models, but not established as an observational fact. After those maps, it was the framework within which all discussion of large-scale structure took place. The picture was, in the precise sense of the word, irreversible. Once the universe had been seen to be organized in this way, it could not be unseen, not because the data was incontrovertible in every detail, but because the overall pattern was too coherent, too consistent across independent surveys, too clearly the product of a physical process rather than a statistical fluctuation. This irreversibility is one of the less discussed features of major scientific discoveries. There is a moment before and a moment after, and the moment after cannot be returned to the moment before, regardless of what subsequent data reveals. The details change. The models are refined. Individual structures are recharacterized as surveys improve. But the basic fact that the universe at large scales is a web of matter surrounding voids became, through those early surveys, one of the established facts of cosmology in the way that the expansion of the universe and the existence of other galaxies had become established facts in the decades before. The surveys that followed the CFA, the Las Campanas redshift survey in the mid-1990s, the 2-degree field galaxy redshift survey at the turn of the millennium, the Sloan Digital Sky Survey across the following decade, and more recently, the Dark Energy Spectroscopic Instrument Survey, each extended the mapped volume, increased the galaxy count by orders of magnitude, and refined the statistical characterization of voids and filaments. Each confirmed the essential picture while adding layers of detail that the earlier surveys could not resolve. The void size function became measurable with statistical precision. The relationship between void properties and the surrounding large-scale structure was quantified. The comparison between observed void populations and the predictions of cosmological simulations became a standard test of structure formation models. The simulations themselves grew in sophistication alongside the surveys. Large computational projects, the Millennium Simulation, the Illustris Project, the Eagle Simulation, and others, modeled the evolution of the universe from near-uniform initial conditions to the present cosmic web, tracking hundreds of millions of particles representing dark matter and ordinary matter across volumes comparable to those covered by the observational surveys. The voids that emerged in those simulations bore a recognizable resemblance to the voids found in the data. Similar size distributions, similar internal density profiles, similar relationships to the surrounding filaments and walls. The resemblance was not perfect. There were, and remain, discrepancies between the observed void population and the simulated one, particularly at the largest scales, where the rarest and most extreme structures are found. Those discrepancies are where the interesting questions live. They are the places where the standard model of cosmology is being quietly interrogated by the data it is supposed to explain. The Boötes void, identified in 1981 in a survey covering a small fraction of the sky with a handful of carefully measured galaxy redshifts, sits in retrospect at the beginning of that interrogation. It was not merely an anomaly to be explained. It was a signal, an early indication that the universe, at its largest scales, was capable of producing structures more extreme than comfortable theory preferred. Understanding what those structures are telling us and what the physics inside them reveals about the universe's most fundamental properties requires looking more carefully at the voids themselves, not just at their boundaries, but at their interiors. Chapter 6: The Cosmic Web and Its Absences. Step back far enough from any complex structure, and its organizing principle becomes visible in a way it cannot be from within. The individual components, whatever they are, at whatever scale, resolve into a pattern. Relationships that were invisible up close declare themselves across the larger view. This is true of cities seen from altitude, of river systems seen from orbit, of neural tissue seen under magnification. And it is true in the most literal sense available to modern science, of the universe seen across its full observable extent. The structure that becomes visible at that scale has acquired a name that is both precise and evocative: the cosmic web. It is a name that earns its second word. The large-scale distribution of matter in the universe is not a cloud, not a gradient, not a collection of isolated objects floating in neutral space. It is a network, a system of interconnected elements whose relationships are as defining as the elements themselves. To understand any part of it fully requires understanding how it connects to the rest. The web is built, at its foundation, from dark matter. The filaments that form its skeleton are primarily dark matter structures, vast, elongated concentrations of the invisible mass that makes up the majority of the universe's matter content. These filaments are not sharp edges, but diffuse gradients, regions where the density of dark matter rises above the surrounding average and draws ordinary matter along with it. Ordinary matter, gas, and eventually stars and galaxies, follows the dark matter's gravitational lead, settling into and along the filaments, tracing their structure in light even where the dark matter itself remains invisible. At the intersections of filaments, where multiple dark matter concentrations converge, the density is highest and the structures most complex. These are the nodes of the web, the great galaxy clusters, where hundreds or thousands of galaxies orbit a common gravitational center, where the intracluster medium glows in X-rays from the heat of infalling gas, where the largest concentrations of ordinary matter in the universe reside. Between the nodes, along the lengths of the filaments, galaxy groups and isolated galaxies trace the thread of the web across hundreds of millions of light-years. And where filaments meet in sheets rather than nodes, galaxy walls form, flat, extended structures like the Great Wall identified in the CFA survey, spanning distances that test the limits of what the word large can meaningfully convey. The voids occupy everything else, and everything else is most of the volume. This is worth holding precisely in mind. The filaments, walls, and clusters of the cosmic web, for all their visual dominance in the maps that astronomers produce, for all the complexity and richness of the physics occurring within them, occupy a relatively small fraction of the total volume of the observable universe. Estimates vary depending on the definition used and the survey examined. But it is broadly accurate to say that voids account for somewhere between 70% and 80% of the universe's total volume. The web, for all its scale, is a structure of threads and nodes. The voids are the space those threads enclose. Understanding the relationship between the web and the voids requires following the flow of matter across cosmic time, not as a metaphor, but as a physical process with a specific direction and a specific driver. Matter does not remain stationary within the large-scale structure. It moves, drawn by gravity from regions of lower density toward regions of higher density. Within a void, the gravitational gradient points outward in every direction, toward the filaments and walls that bound the void on all sides. Gas and dark matter that begins inside a void, in the relatively modest initial underdensity that the void started as, gradually flows along those gradients, moving toward the denser surrounding structures. Over billions of years, this drainage evacuates the void interior, progressively reducing its density and sharpening the contrast between the void and its boundaries. This means that voids are not static. They are dynamic structures, evolving over cosmic time in a specific and predictable direction. They grow emptier, and they grow larger. As matter drains outward from the void interior toward the bounding filaments, the effective boundary of the void, the surface at which the density drops below whatever threshold defines the void's edge, moves outward as well. Voids expand. They do so not because space inside them is expanding faster in some absolute sense, but because the evacuation of matter makes the underdense region progressively larger. In the far future, as the universe ages and matter continues to drain along filaments into clusters, the voids will be more extensive and more deeply empty than they are today. This evolutionary trajectory is the flip side of the growth of structure. The clusters that will eventually form from the continued infall of matter along filaments will be richer, more massive, more gravitationally dominant. The voids they draw that matter from will be correspondingly emptier. The contrast between the densest and the most diffuse regions of the universe increases with time, driven by gravity's relentless amplification of whatever density differences already exist. The cosmic web is not a finished structure. It is a process, one that began with the first density fluctuations after the Big Bang, and will continue in some form as long as matter and gravity coexist. The hierarchical nature of this process leaves a hierarchical imprint on the void population. Just as the initial density field contained fluctuations on all scales, from the smallest structures that gravity could amplify to the largest modes of variation in the early universe, the voids that form from that field exist across a corresponding range of scales. Large voids, hundreds of millions of light-years across, dominate the visual impression of the maps. But within those large voids, the density is not perfectly uniform. There are subregions that are slightly denser than the void average. Density fluctuations that, while too small to form significant galaxy concentrations, are nonetheless present and detectable. And within the deepest underdense subregions of a large void, smaller voids can be identified in their own right. Regions underdense relative to the already underdense void interior in which they sit. This nesting, large voids containing smaller voids, which contain smaller ones still, is called void hierarchy, and it is a direct reflection of the hierarchical nature of the initial density field itself. The hierarchy of voids is not merely a geometric curiosity. It carries information about the statistical properties of the initial density fluctuations, the primordial power spectrum, in a way that complements what can be learned from the distribution of galaxies and clusters. Each level of the hierarchy reflects a different scale of initial variation, amplified and evolved by gravity into the structures visible today. Reading the hierarchy correctly means reading something fundamental about the conditions that existed in the universe's earliest moments, before any structure had formed at all. This connection between the present void population and the primordial initial conditions is one of the reasons cosmologists have invested considerable effort in developing precise methods for identifying and characterizing voids at multiple scales simultaneously. A catalog of only the largest voids tells part of the story. A catalog that extends down through the hierarchy, identifying the subvoids within voids and the structures within those, tells a richer one, more tightly connected to the underlying physics of structure formation. The practical challenge is significant. Identifying subvoids within voids requires survey data of sufficient depth and resolution to detect the relatively sparse galaxy populations inside large underdense regions. If a large void contains only a handful of galaxies per unit volume, the statistical sample available for identifying substructures within it is correspondingly limited. The deeper and more complete the survey, the further down the hierarchy it is possible to probe. This is one of the scientific drivers behind the increasingly ambitious galaxy surveys of the present and near future. Not just the desire to map more volume, but the desire to map existing volume more completely, reaching fainter galaxies and sparser environments. Modern surveys have identified thousands of voids across a wide range of scales. The precise number depends on the survey, the void-finding algorithm, and the minimum size threshold applied. But the population is large enough that statistical analyses of void properties can be carried out with considerable confidence. The void size function, the distribution of how many voids of each size exist within a given survey volume, has been measured from multiple independent surveys and compared to the predictions of cosmological simulations. The agreement is generally good, reflecting the success of the standard model of structure formation in capturing the broad features of void statistics. The discrepancies, where they exist, are at the extremes: the largest voids, the emptiest interiors, the sharpest boundaries, the places where the rarest structures live, and where the statistics of small samples make precise comparison difficult. What the void population reveals about the universe's statistical properties goes beyond the size function alone. The shapes of voids carry information as well. In a universe governed purely by gravity, operating on an isotropic background, voids would tend toward roughly spherical shapes. The isotropic gravitational field would drain matter outward equally in all directions. But in the real universe, voids are embedded in the cosmic web, bounded by filaments and walls that are not symmetrically distributed around every void. The tidal gravitational field of the surrounding structure distorts the void as it grows, stretching it in some directions and compressing it in others. The result is that real voids are not spheres but triaxial ellipsoids, elongated structures whose shape reflects the anisotropic environment in which they evolved. This shape distortion has an observational consequence that astronomers have turned into a cosmological tool. When a void is viewed along the line of sight in a redshift survey, its apparent shape is affected not only by the physical distortion from tidal forces, but also by a separate effect called redshift space distortion. Galaxies near a void, moving under the influence of the void's gravitational field, have peculiar velocities directed away from the void center, flowing outward as part of the general evacuation of the void interior. These peculiar velocities add to or subtract from the galaxy's cosmological redshift, distorting the apparent shape of the void along the line of sight relative to its true three-dimensional shape. By measuring this distortion statistically, comparing the apparent shapes of voids in redshift space to their expected true shapes, cosmologists can measure the rate at which structure is growing, which is itself a sensitive function of dark energy and the geometry of space-time. This technique, called the Alcock-Pazinski test applied to voids, is among the most elegant in contemporary cosmology. It requires no assumptions about the intrinsic properties of individual voids. It requires only that the statistical distribution of void shapes in the plane of the sky and along the line of sight be compared, and that the cosmological model predict the correct ratio. Deviations from the predicted ratio signal either incorrect cosmology or systematic effects in the data, and disentangling the two is a substantial part of the work of modern void cosmology. The filaments that bound voids are as scientifically interesting as the voids themselves, and the two cannot be fully understood in isolation. A filament is not merely the edge of a void. It is simultaneously the edge of the void on one side and the edge of a different void on the other. Every filament in the cosmic web separates two or more underdense regions, and its properties, its mass, its length, its galaxy content, are shaped by the voids that press against it from both sides, as much as by the clusters it connects. The cosmic web is, in this reading, as much a void network as a filament network. The filaments are the boundaries, the voids are the domains. This reframing, treating the voids rather than the filaments as the primary structures, is not merely a semantic preference. It has practical implications for how large-scale structure is analyzed and what features are emphasized. A void-centric view of the cosmic web draws attention to properties that a filament-centric view can obscure: the topology of the underdense regions, the connectivity of the void network, the way voids merge and subdivide across cosmic time. These properties carry cosmological information that complements what filament and cluster statistics provide, and they are increasingly being incorporated into the standard toolkit of large-scale structure analysis. The universe, viewed this way, is a structure defined as much by its absences as by its presences. The voids are not the background against which the cosmic web is drawn. They are half of what the web is. The interior volumes whose evacuation created the filaments, whose growth measures dark energy, whose hierarchy encodes the initial conditions of the cosmos. The web cannot be understood without them, and they cannot be understood without the web. They are, in the most fundamental sense, the same thing seen from different vantage points. That understanding deepens considerably when attention turns to the most extreme examples, the voids that push against the outer limits of what standard cosmology predicts should exist at all. Chapter 7. The Boötes Void and Beyond. There is a difference between something being rare and something being improbable. Rare means it does not occur often. Improbable means it should not occur at all, given the rules governing the system in which it appears. Most of the time, in ordinary experience, the distinction does not matter much. but in cosmology, where the rules are precise, where the initial conditions are constrained by independent measurements, and where the structures that form from those conditions can be compared directly to theoretical predictions. The distinction between rare and improbable becomes one of the most consequential questions a scientist can ask. The Boötes void sits at the center of that question. When Kirshner and his colleagues identified the underdensity in Boötes in 1981, the scientific discussion that followed focused primarily on its reality, on whether the apparent absence of galaxies in that region of the survey reflected a genuine physical underdensity or some artifact of the survey methodology. As subsequent observations confirmed the void's existence and refined its dimensions, the discussion shifted to its size. By the best current measurements, the Boötes void extends across a region of roughly 300 to 330 million light-years in its longest dimension. Its interior contains a small number of galaxies. Estimates vary, but the count is dramatically below what the surrounding density would predict for a region of that volume. The void is not perfectly empty, but it is emptier by a very significant margin than the standard model of structure formation suggests a region of that size should be. The question of whether this makes Boötes genuinely anomalous, or merely a rare but not improbable outcome of standard cosmological processes, has been debated for decades without a fully satisfying resolution. The difficulty lies in the statistics. The universe is large. The observable portion alone spans tens of billions of light-years, and rare events, by definition, do occur somewhere. If the probability of finding a void as large and as empty as Boötes in any given survey volume is small but non-zero, then finding one is not evidence that the underlying model is wrong. It is simply evidence that the survey happened to sample a particularly unusual region. This argument is logically sound, but scientifically uncomfortable. It cannot be definitively refuted because the universe does not provide a control group. We have one observable universe, and we cannot determine how typical our particular realization of it is. What can be done is to run cosmological simulations, large computational models of structure formation that begin from observed initial conditions and evolve forward according to the laws of physics, and ask how frequently those simulations produce voids as large and as empty as Boötes. If the answer is very rarely, even across many independent simulations of the same volume, then Boötes remains at minimum a statistical outlier. And its existence places pressure on the models, even if it does not definitively falsify them. The results of such comparisons have been mixed in a way that is itself informative. Early simulations, run with limited resolution and relatively small volumes, rarely produced Boötes-scale voids. As simulations improved in scale and resolution, the occasional very large void appeared, but typically with internal density profiles somewhat less extreme than what observations suggested for Boötes. The void was not impossible within the standard framework. But it was not comfortably predicted by it either. It occupied a position at the tail of the distribution, present in simulations, but infrequently, and with properties that placed it near the boundary of what the physics was expected to produce. This boundary is scientifically interesting, precisely because it is where the model is most constrained. The bulk of the void population, the thousands of moderate-sized, underdense regions identified in modern surveys, is well reproduced by standard simulations. The agreement there is good enough that voids in that size range can be used as precision cosmological probes with confidence in the underlying theory. But the extreme end of the distribution, where the largest and emptiest voids live, is where the model's predictions are most uncertain and where genuine tension between theory and observation is most likely to be informative. Boötes is not alone at that extreme. Modern surveys have identified other large, underdense regions that, while not always as dramatically empty as Bootes, contribute to a growing sense that the very largest voids in the observable universe may be slightly more common or slightly more extreme than standard simulations predict. Whether this represents a genuine failure of the standard model, a systematic effect in the observations, or simply the expected statistical scatter in a finite universe remains an open question, one that more precise surveys and more sophisticated simulations are actively working to answer. The most intriguing of the potential supervoids is associated not with a galaxy survey, but with the oldest light in the universe, the cosmic microwave background. The thermal radiation released when the universe was approximately 380,000 years old has been mapped with extraordinary precision by a series of space-based observatories, most recently the Planck satellite. Those maps are, to an excellent approximation, featureless. The temperature variations across the sky are tiny, and they follow statistical patterns consistent with the predictions of inflation and the standard cosmological model. But there is one region of the CMB sky that has attracted sustained attention because it does not quite fit the expected pattern. In the direction of the constellation Eridanus, there is a region of anomalously low temperature, a cold patch roughly 5 degrees across in angular size, significantly colder than the surrounding CMB and colder than can be easily explained by the standard statistical distribution of primordial fluctuations alone. This feature, known as the CMB cold spot, was identified in early analyses of the WMAP satellite data and confirmed by subsequent observations. Its origin remains genuinely contested. Several explanations have been proposed. One is statistical, that the cold spot is simply an unlikely fluctuation in the primordial temperature field, the kind of rare deviation that will occasionally appear in a map of sufficient size even when the underlying distribution is normal. Another invokes the integrated Sachs-Wolf effect discussed earlier. If there is a very large supervoid in the direction of the cold spot, CMB photons passing through it would lose a small amount of energy as they traverse the unusually weak gravitational potential, producing precisely the kind of temperature decrement observed. The supervoid hypothesis for the CMB cold spot is not merely speculative. It makes a specific, testable prediction. There should be a large, underdense region in the direction of Eridanus at a redshift corresponding to the epoch at which the integrated Sachs-Wolf effect would be most efficient at imprinting a temperature signal on the CMB. Several galaxy surveys have examined that region of the sky specifically to test this prediction. And the results have been tantalizing without being conclusive. A 2015 study using data from the Pan-STARRS survey and the WISE infrared satellite identified a significant underdensity in the direction of the cold spot, a region roughly 1.8 billion light-years across, with a galaxy density substantially below the cosmic average. The scale of this structure, if confirmed as a coherent physical void rather than a statistical alignment of smaller underdensities along the line of sight, would make it one of the largest voids ever identified. Its authors argued that the integrated Sachs-Wolf effect from such a structure could account for a meaningful fraction of the cold spot's temperature decrement. Subsequent analyses, using different surveys and different statistical methodologies, have reached varying conclusions, some supporting the supervoid interpretation, others finding the evidence insufficient to prefer it over a purely statistical explanation. This inconclusiveness is not a failure of the science. It is a reflection of the genuine difficulty of the measurement. The signal produced by a supervoid on the CMB is small. The integrated Sachs-Wolf effect is inherently a weak imprint, requiring careful subtraction of other contributions to the CMB temperature field before it can be cleanly detected. The surveys needed to characterize the galaxy distribution in the relevant region require substantial observational resources. And the statistical question, Whether the cold spot's properties are consistent with a primordial fluctuation, a supervoid effect, or some combination, is sensitive to assumptions about the background cosmological model against which the anomaly is evaluated. What the cold spot discussion illustrates, beyond its specific content, is the way extreme structures force cosmology to engage simultaneously with multiple layers of uncertainty. There is uncertainty about the observation itself, about the precise properties of the anomalous feature. There is uncertainty about the astrophysical mechanism, about whether the integrated Sachs-Wolf effect from a given void would produce a signal of the observed magnitude. And there is uncertainty about the statistical context, about how to correctly assess the probability of the feature given everything else known about the universe. Resolving any one of these uncertainties requires progress on the others, which is why the cold spot has remained an active area of research for more than 2 decades without reaching a definitive conclusion. The broader lesson from both Bootes and the cold spot is that the extreme end of any distribution in nature carries disproportionate scientific weight. The typical cases, the moderate-sized voids, the average density fluctuations, confirm what the model already predicts. The extreme cases test where the model's predictions become uncertain, where the physics is least constrained by existing data, and where genuine surprises are most likely to be found. A cosmological model that correctly predicts the statistical properties of 10,000 moderate voids, but fails to account for the handful of supervoids at the largest scales, is not simply wrong in a minor detail. It may be missing a physical ingredient whose effects are too small to matter in ordinary environments, but become significant precisely at the extremes. One candidate for such an ingredient is, again, dark energy. The largest voids are the environments where dark energy's influence is least opposed by gravity, and where the growth of underdense regions over cosmic time is most sensitive to dark energy's properties. If dark energy is not a cosmological constant, not a fixed, uniform property of space, but instead a dynamic field whose strength varies over time or across space, then its effects would be most pronounced in the largest voids, where the competing influence of matter density is weakest. The supervoids, in this reading, are the regions where a dynamical dark energy would leave its clearest signature, and where the current data, while not conclusive, leaves room for exactly the kind of deviation that a dynamical model might predict. This is speculative, in the precise scientific sense. It is a hypothesis consistent with available data, but not yet confirmed by it. The confirmation, if it comes, will require the next generation of surveys, projects currently underway or in development that will map the three-dimensional distribution of galaxies across much larger volumes and to much greater depths than have been achieved before. The Dark Energy Spectroscopic Instrument, which began science operations in 2021 and is conducting the largest galaxy redshift survey in history, will provide void catalogs of unprecedented statistical power. The Euclid Space Telescope, launched in 2023, will extend this mapping into the near-infrared and across a significant fraction of the sky. The Vera Rubin Observatory's Legacy Survey of Space and Time will add photometric depth that complements the spectroscopic surveys. Each of these projects will, among many other scientific goals, improve the characterization of the extreme void population, the supervoids and near-supervoids that sit at the boundary of current understanding. They will test whether the size and emptiness distributions of the largest voids are consistent with standard predictions, and with what precision. They will search for more structures like Bootes, and determine whether the Bootes void is genuinely exceptional or simply the most prominent member of a class of structures that the standard model can accommodate with appropriate adjustment of its parameters. What they will not do, almost certainly, is make the extreme voids less interesting. The history of cosmological surveys suggests the opposite, that every increase in observational power reveals new features at the boundaries of the known, new structures that push against whatever model was current at the time of their discovery. The universe has a consistent record of exceeding the imagination of its observers at the edges, of placing, at the limits of the available data, structures and phenomena that require the model to stretch. The Boötes void was one such structure. The cold spot may be pointing toward another. Whether future surveys resolve these anomalies into comfortable agreement with extended versions of the standard model, or whether they reveal something more fundamentally unexpected, is a question that the data will eventually answer. For now, they stand as reminders that the largest scales of the universe are not yet fully legible, that the map, however detailed it has become, still has regions where the writing grows uncertain. Those regions of uncertainty are not obstacles to understanding. They are its leading edge. And understanding what the emptiness is actually made of, what physical processes govern its interior and determine its evolution, brings that edge into sharper focus. Chapter 8. What emptiness is made of. The interior of a cosmic void is not a place where physics stops. It is a place where a particular balance of physical forces, one that exists nowhere else in the observable universe with quite the same clarity, becomes the governing condition of everything within it. To enter a void, conceptually, is not to leave the domain of physical law. It is to encounter those laws operating in an unusually pure register, stripped of the noise and complexity that matter density introduces everywhere else. Consider what the interior of a large void actually contains in physical terms. There is space, vast expanding space, stretching in every direction toward boundaries hundreds of millions of light years away. There is the cosmic microwave background, filling the void as it fills all of space, a faint thermal presence that permeates everything. There is a weak gravitational field, pointing outward in every direction toward the denser surrounding structures, gently accelerating whatever matter remains inside toward the void's boundaries. There is dark matter, present but sparse, insufficient to generate the kind of gravitational collapse that would produce significant structure. And there is dark energy, not concentrated here, not stronger here in any absolute sense, but relatively more dominant here than anywhere else in the universe, because the competing influence of matter-gravity is so greatly reduced. This relative dominance is the defining physical characteristic of void interiors. Dark energy, in the current understanding, is associated with the vacuum itself, with the energy content of empty space. It does not dilute as space expands. It does not concentrate where matter concentrates. It is, to the best of current measurement, uniform across the universe. But its effects are not uniform, because those effects must always be weighed against the competing influence of matter's gravity. In a dense cluster, gravity is so strong that dark energy's expansive influence is locally irrelevant. The cluster holds together, evolving according to gravitational dynamics that dark energy cannot meaningfully perturb. In a void, the balance is reversed. Gravity is weak, matter is sparse, and dark energy's influence on the local geometry of spacetime is as unobstructed as it ever gets. This makes voids, in a precise physical sense, the most dark energy-dominated environments accessible to observation. They are regions where the universe's accelerating expansion, driven by dark energy, expresses itself most purely, least obscured by the gravitational effects of matter. And because dark energy's nature is one of the most pressing unsolved problems in fundamental physics, the environments where it dominates most clearly are the environments with the greatest potential to reveal its properties. The growth rate of voids over cosmic time is the primary channel through which this potential is realized. As voids expand, as matter continues to drain from their interiors toward the surrounding filaments, and the dark energy drives the overall expansion of space, their size increases at a rate that depends on the balance between gravity and dark energy. If dark energy is a cosmological constant, this growth rate follows a specific predicted trajectory. If dark energy is instead a dynamic field, one whose energy density changes over time, strengthening or weakening as the universe ages, then the growth rate deviates from that trajectory in ways that should, in principle, be detectable with sufficiently precise measurements. The measurement itself is not straightforward. Determining how the void size distribution has changed between, say, 5 billion years ago and today requires comparing void populations at different redshifts, different epochs in cosmic history, while accounting for the many ways in which survey selection effects, galaxy bias, and observational limitations can mimic or obscure a genuine cosmological signal. The techniques for doing this have been developed over roughly 2 decades of methodological work, and they are now precise enough that current and upcoming surveys can use void growth rates as genuine constraints on dark energy models, complementary to the supernova distance measurements and baryon acoustic oscillation analyses that have traditionally dominated this area of cosmology. What makes the void growth rate particularly valuable as a probe is its sensitivity to the relationship between the expansion of space and the growth of structure, a relationship that differs between general relativity and proposed modifications of gravity. Several theoretical frameworks that attempt to explain dark energy by modifying Einstein's equations at large scales, rather than introducing a new energy component, predict void growth rates that differ from the standard cosmological constant model in characteristic ways. Measuring void growth with sufficient precision can therefore discriminate not just between different dark energy models, but between different theories of gravity operating at cosmological scales. Gravity itself, in other words, is being tested inside the voids. This is not a metaphor. Modified gravity theories, frameworks in which the behavior of gravity at large scales or low densities differs from general relativity's predictions, often produce their largest deviations from standard behavior in precisely the low-density environments that voids represent. A scalar field that modifies gravity might be screened in dense environments, its effects suppressed by the high matter density, but unscreened in the sparse interior of a void, where the field can express its full influence on the dynamics of matter and expansion. Several specific modified gravity proposals have this property, and voids have been identified as among the most promising places to look for their signatures. This is a significant conceptual shift from the early decades of void science, when voids were studied primarily as features of large-scale structure rather than as laboratories for fundamental physics. The shift has been driven partly by theoretical developments, the realization that void interiors offer genuinely unusual physical conditions, and partly by the increasing precision of observational data, which has made it possible to extract meaningful constraints from void statistics rather than merely describing them qualitatively. The result is that the void, once the overlooked negative space of the cosmic map, has become one of the more productive environments in contemporary cosmological research, not because it contains the most matter or the most energy, but because what it contains is arranged in a configuration that makes certain physical signals legible that would otherwise be buried under the complexity of denser environments. Among the most remarkable inhabitants of void interiors are the galaxies that form and evolve there. Not the thousands of galaxies that populate a rich cluster, nor the hundreds that trace a filament, but the handful of dwarf galaxies scattered across volumes that would, in a denser region of the universe, host entire galaxy groups. These void galaxies are among the most isolated objects known to exist, and their isolation has shaped them in ways that make them scientifically distinctive and, in a quieter register, philosophically striking. A galaxy that forms inside a large void does so in conditions fundamentally different from those experienced by the overwhelming majority of galaxies in the observable universe. It has access to a limited reservoir of gas, the sparse material that remained within the void after the general evacuation that created the underdensity. It has few neighbors close enough to exert significant tidal influence. It is not subject to the ram pressure stripping that removes gas from galaxies moving through the hot intracluster medium of a dense environment. It does not experience the close encounters and mergers that disrupt galactic structure, trigger bursts of star formation, and redistribute angular momentum in galaxies embedded in filaments and walls. It evolves, to a degree unusual in the universe, in something approaching isolation. The consequences of this isolation are visible in the properties of void galaxies as a population. They tend to be bluer than average, a signature of ongoing star formation, which produces the hot, luminous, short-lived stars that emit disproportionately in the blue end of the spectrum. This is somewhat counterintuitive. One might expect that galaxies with access to less gas would form fewer stars. But the processes that shut down star formation in more typical galaxies, the environmental interactions, the stripping of gas reservoirs, the heating of infalling material by a hot cluster atmosphere, are largely absent in voids. Void galaxies retain their gas, consume it slowly, and continue forming stars at a modest but sustained rate that their counterparts in denser environments have often long since ceased. They also tend to be morphologically simpler. The complex asymmetric structures that result from gravitational interactions, the tidal tails, the disturbed disks, the multiple nuclei that indicate recent mergers, are rare in void galaxies. They are more likely to be regular, symmetric, undisturbed, closer in some respects to a naive picture of what an isolated galaxy in its native dark matter halo should look like, without the environmental modifications that complicate the interpretation of galaxies everywhere else. In this sense, void galaxies are not merely interesting objects in themselves. They are reference objects, baseline examples of galaxy evolution in the absence of environment, against which the environmental effects visible in denser regions can be more clearly identified and quantified. The study of void galaxies has grown into a substantial subfield of observational astronomy, driven by the recognition that understanding galaxy formation requires disentangling intrinsic properties from environmental ones. A galaxy in a cluster is the product of its initial conditions, its formation history, and everything that has happened to it in its dense, interactive environment. A void galaxy is the product of its initial conditions and its formation history, with the environmental variable largely controlled. Comparing the two populations, holding everything else as constant as the data allows, isolates the environmental contribution to galaxy properties, which turns out to be significant across a wide range of observable characteristics. Dark matter halos surrounding void galaxies have their own distinctive properties. In denser environments, halos grow through mergers and accretion. They accumulate mass from neighboring halos and from the diffuse dark matter of their surroundings, building up over time through a complex assembly history. Void halos, by contrast, grow more slowly and more quietly, with fewer mergers and a simpler assembly history that reflects the sparse environment. The halos of void galaxies tend to be less concentrated, more diffuse in their mass distribution than halos of comparable mass in denser environments, a signature of the quieter gravitational history they have experienced. This difference in halo concentration has observable consequences for the dynamics of the galaxies they host. And comparing void and field galaxy dynamics offers a way to test predictions about the relationship between halo structure and galaxy properties that is difficult to isolate in more crowded environments. The void itself, considered as a physical system, has a property that connects all of these individual features into a coherent picture. It is a region defined by its relationship to what surrounds it, a domain whose interior conditions are set by the evacuation of matter toward its boundaries. The galaxies inside it, the dark matter halos, the gas, the gravitational field, All of these reflect, in different ways, the history of that evacuation and the resulting underdensity. The void is not a random sample of the universe. It is a region selected by its own formation history to be systematically different from the cosmic average in ways that are physically meaningful and observationally exploitable. This coherence is what makes voids, as scientific objects, more than the sum of their measurable properties. They are environments with a character, a consistent set of conditions that follows from their defining physical situation and that propagates through every aspect of what they contain. The low matter density, the dark energy dominance, the slow halo assembly, the isolated galaxies, the unscreened modified gravity signals, all of these are expressions of the same underlying fact, which is that matter has left and not returned, and that in its absence, the universe looks and behaves differently than it does anywhere else. Understanding that difference, mapping it precisely, comparing it to theoretical predictions, using it to constrain the fundamental parameters of cosmology, is the work of void science as it currently stands. It is work that is incomplete in productive ways, pointing toward measurements not yet made and models not yet fully tested. The voids are telling a story about dark energy, about gravity, about the initial conditions of structure formation, and about the evolution of galaxies across cosmic time. The story is not yet fully transcribed. But there is another dimension to the void story that has nothing to do with distant surveys or abstract cosmological parameters. It concerns where we sit within the large-scale structure. The question of whether our own cosmic address places us inside one of the structures described in this journey, or somewhere else entirely. The answer, when it came, was not what most cosmologists had expected. Chapter 9. The Void Inside the Address. Every object in the universe has a location, and every location exists within a context that shapes what happens there. A galaxy in a rich cluster experiences a different gravitational environment, a different thermal history, a different rate of interaction with neighbors than a galaxy in a filament, or in a wall, or in the sparse interior of a large void. Context, in cosmology, as in most domains of understanding, is not incidental. It is constitutive. Where something is, determines, in part, what it is and how it evolves. For most of modern astronomy, the question of where the Milky Way sits within the large-scale structure of the universe was treated as essentially settled in its broad outlines. Our galaxy is part of the local group, a modest collection of roughly 80 galaxies, dominated by the Milky Way and the Andromeda Galaxy, bound together by gravity and moving as a unit through the larger universe. The local group sits near the edge of the Virgo supercluster, a concentration of galaxy groups and clusters extending across roughly 110 million light-years. Beyond the Virgo supercluster lies the larger structure now called the Laniakea supercluster, a gravitational basin of attraction spanning approximately 500 million light-years, within which the local group's motion can be understood as a slow drift toward the Great Attractor, a region of high mass concentration in the direction of the constellation Centaurus. This address, local group, Laniakea supercluster, broader cosmic web, was understood to place the Milky Way in a moderately underdense region of the universe, not embedded in a rich cluster, but not isolated in a deep void either. A middling position in the cosmic hierarchy, neither extreme in its richness nor extreme in its emptiness. That understanding was reasonable given the data available. It was also, as a 2013 analysis suggested and subsequent work has developed in more detail, potentially incomplete in a significant way. The structure now referred to as the KBC void, named for the three astronomers who identified and characterized it, Ryan Keenan, Amy Barger, and Lennox Cowie, is not a small local underdensity. It is, by the most careful current estimates, a region of underdensity extending across approximately 2 billion light-years, centered on or near our own position in the universe. Its underdensity is not as extreme as the interior of the Bootes void. The KBC underdensity is more moderate, perhaps 20 to 30% below the cosmic average, rather than the 70 to 90% deficit of the most dramatic voids. But its scale, if the structure is as large and as coherent as the evidence suggests, would make it one of the largest underdense regions identified anywhere in the observable universe. The identification of the KBC void rested primarily on counts of galaxies in various directions and at various distances from our position, a method that requires careful control of selection effects and survey completeness, since an apparent underdensity could in principle reflect a deficiency in survey coverage rather than a genuine deficit of galaxies. Keenan, Barger, and Cowie were careful to account for these possibilities, and the underdensity they identified survived the tests they applied to it. Subsequent work by other groups, using independent data and different methodological approaches, found results broadly consistent with the original analysis, though the precise extent and depth of the underdensity continue to be refined. If the KBC void is real as characterized, and the current balance of evidence suggests it is, though uncertainties remain, then our position within it has a consequence that connects the local cosmic environment to one of the most actively debated problems in contemporary cosmology. That problem is the Hubble tension. The Hubble constant, the number that describes how fast the universe is expanding, measured in kilometers per second per megaparsec of distance, is one of the most fundamental parameters of the standard cosmological model. Its value can be measured in two independent ways. The first uses the cosmic microwave background and the physics of the early universe, the acoustic oscillations imprinted in the CMB and in the large-scale distribution of galaxies, to infer the expansion rate from first principles within the standard model. The second uses the local universe, distances to nearby galaxies measured through a chain of calibrated standard candles, from Cepheid variable stars to Type 1a supernovae, to measure the expansion rate directly from the recession of observed objects. Both measurements are now precise. Both are robust against known systematic effects. And they disagree. The CMB-based measurement gives a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec. The local distance ladder measurement gives approximately 73 kilometers per second per megaparsec. The discrepancy is roughly 9%, and its statistical significance, now above 5 sigma, the conventional threshold for a definitive result in physics, is sufficient that it cannot be dismissed as a measurement error without a specific identified source of systematic bias that has so far not been found. The Hubble tension is, in the precise language of physics, a crisis in the standard model, an inconsistency between two well-established measurements that the model, as currently formulated, cannot reconcile. Several proposed resolutions have been put forward: modifications to the physics of the early universe, new relativistic species of particles, early dark energy that alters the sound horizon before recombination. Most of these proposals require adding new physical ingredients to the standard model in ways that have their own observational consequences and that are constrained by other data. The KBC void offers a different kind of resolution, one that does not require modifying the fundamental physics, but instead questions whether the local measurement of the Hubble constant is being made from a representative location. If the Milky Way is embedded in a significant underdensity, then the local expansion rate, measured from the motion of galaxies within and just beyond that underdensity, would be higher than the global average. Matter drains out of voids, as we have seen, flowing toward the denser surrounding structures. This outflow adds a systematic component to the velocities of galaxies near the void boundary, a bulk flow directed away from the void center, that would be interpreted, if not accounted for, as an elevated local Hubble constant. The quantitative question is whether the KBC void is large enough and deep enough to account for the full magnitude of the Hubble tension, to explain the 9% discrepancy between local and CMB-based measurements through the local outflow of matter from the underdense region in which we are embedded. Several research groups have attempted to answer this question, with results that are suggestive but not yet definitive. A 2020 study by Hochschild and Barger showed that the density profile of the KBC void, as characterized from galaxy counts, was consistent with producing a local Hubble constant elevated by roughly 5 to 8% above the global average, a contribution that would account for a significant fraction and possibly the majority of the observed tension. Other analyses have found similar results using independent approaches. The void outflow hypothesis does not require exotic new physics. It requires only that the standard gravitational dynamics of structure formation, operating on the large underdensity in which we are situated, produce a systematic elevation of locally measured recession velocities relative to the global expansion rate. This resolution, if correct, would be both satisfying and disquieting in equal measure. Satisfying because it would dissolve one of cosmology's most pressing current anomalies without requiring modifications to the Standard Model's fundamental physics. Disquieting because it would mean that our measurements of the local universe, the measurements used to calibrate the distance ladder and determine the local Hubble constant, have been systematically biased by our position within a large underdensity, without that bias being recognized or corrected for in the decades during which the Hubble constant was being refined. It would mean, in other words, that where we are has been shaping what we measure in ways we did not fully account for. This is not an unfamiliar lesson in the history of astronomy. The history of cosmological measurement is, in part, a history of recognizing and correcting for the ways in which the observer's position introduces bias into the observation. Hubble's original measurements of the expanding universe were complicated by the fact that nearby galaxies have peculiar velocities, motions relative to the Hubble flow driven by local gravitational dynamics, that needed to be separated from the cosmological signal. The calibration of the distance ladder has been refined repeatedly as each rung was found to carry systematic uncertainties not initially recognized. The recognition that the Milky Way is not at the center of the local group, and that the local group is not at the center of the Virgo supercluster. Each required adjustments to how motions were interpreted. The KBC void hypothesis would be the next entry in that series. A recognition that our position within the large-scale structure of the universe is not cosmically neutral, that the underdensity surrounding us introduces a systematic effect on the most fundamental measurement of cosmic expansion, and that accounting for this effect requires characterizing the void in which we are embedded with the same precision applied to the measurements themselves. This places void science in an unexpected relationship with the Hubble tension. What began as a debate about the properties of distant, abstract underdensities has become, through the identification of the KBC void, directly relevant to one of the most consequential unsolved problems in contemporary physics. The voids are not merely features of the distant universe that cosmologists study from a safely external vantage point. We are, it appears, inside one. And that fact has consequences for how we read the universe around us. The history of humanity's understanding of its own position in the cosmos has moved, with remarkable consistency, in a single direction, toward decentering. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the local group. The local group is not the center of Laniakea, and Laniakea is not the center of anything in particular. Each of these recognitions required a revision, not just of the scientific picture, but of the implicit assumption that the observer occupies a privileged or representative position. The KBC void continues that sequence in a subtler but equally significant way. It suggests that our cosmic neighborhood is not merely non-central, but actively atypical, that we are embedded in one of the largest underdense structures in the observable universe, and that this embedding has shaped the cosmological measurements made from our position in ways that are only now being carefully examined. We are not observers standing outside the large-scale structure, measuring it objectively. We are inside it, situated within one of its most unusual features, looking outward through the lens of our particular location. There is a specific quality to this recognition that distinguishes it from the earlier decenterings. When Copernicus removed the Earth from the center of the solar system, or when the Milky Way was understood to be one galaxy among billions, the revision was primarily about scale, about recognizing that the universe was larger and more populous than previously believed. The revision implied by the KBC void is about context rather than scale. It is about the environment in which our measurements are made, and about the ways in which that environment, its density, its dynamics, its relationship to the surrounding cosmic web, introduces a systematic perspective into observations that were assumed to be globally representative. The local expansion rate we measure is higher than the global rate because we are in a region that matter is leaving. The galaxies we see around us are, on average, receding slightly faster than galaxies at comparable distances in a denser region of the universe would recede, because the outflow from the void adds a systematic component to their velocities. Our view of the Hubble constant is, in this reading, a view from a particular place, a place selected by its own formation history to be underdense and whose underdensity inflects the cosmological signal in a specific, calculable direction. This does not diminish the measurements. It contextualizes them. It adds a layer of understanding that was previously missing, an understanding of how the observer's position within the large-scale structure of the universe shapes the universe that the observer sees. And it returns the story, after its long journey through distant surveys and abstract physics, to the most fundamental question in all of observational science. What does it mean to look at the universe from here? The answer, it turns out, depends on knowing where here actually is, and on understanding that here is not empty in the colloquial sense, but embedded within a structured, dynamic, physically meaningful absence that connects our local measurements to the deepest properties of the cosmos. Chapter 10. The Silence That Holds Structure. There is a particular kind of understanding that arrives not as a single insight, but as a slow reorientation, a gradual shift in which the same facts, arranged in the same order, begin to mean something different than they did before. The facts about cosmic voids have not changed in the course of this journey. The universe is mostly empty at large scales. That emptiness is structured, hierarchical, and physically active. It's seeded by the same initial conditions that produced everything else, evacuated by the same gravity that built the filaments and clusters at its boundaries, and dominated by the same dark energy whose nature remains one of the deepest open questions in physics. None of this is new information. What changes, across the course of a careful examination, is the weight assigned to it, the recognition that the emptiness is not peripheral to the story of the universe, but central to it, in a way that the history of cosmology took a long time to make fully visible. Begin at the beginning, not of this documentary, but of the universe itself. In the first fractions of a second after the Big Bang, the cosmos was a nearly uniform plasma of extraordinary density and temperature, threaded with quantum fluctuations so small that calling them tiny understates the case. The density variations at that moment were of order 1 part in 100,000, deviations so slight that any instrument we could imagine placing in that early universe would have struggled to detect them against the overwhelming uniformity of the background. And yet those fluctuations were the seeds of everything. Every galaxy, every cluster, every filament, every wall, and every void in the observable universe grew from those initial perturbations, amplified over 13+ billion years by the consistent, patient operation of gravity. The process of amplification is not symmetric in the way everyday intuition might suggest. It is not the case that overdense regions grew and underdense regions simply stayed where they were, neither growing nor shrinking. Both kinds of region evolved actively, driven by the same physics, but in opposite directions. Overdense regions attracted matter, grew denser, collapsed into progressively more concentrated structures, halos, galaxies, clusters. Underdense regions repelled matter, in the sense that the gravitational gradient within them pointed outward toward denser surroundings, and the matter they initially contained gradually drained toward those surroundings, leaving the interior progressively emptier. The universe did not simply build structures into empty space. It built structures and emptiness simultaneously, as two expressions of the same gravitational dynamics operating on the same initial field. This simultaneity is the conceptual core of everything the voids represent. They are not the leftovers of structure formation, the space that remained after matter had assembled itself elsewhere. They are the active counterpart of structure formation, the regions that became what they are through the same process at the same time for the same physical reasons. To understand why clusters exist is, at a fundamental level, to understand why voids exist. The explanation is identical. Gravity amplifies density contrasts, and density contrasts exist on both sides of the cosmic average. Dark energy enters this story at a specific point in cosmic history, roughly 6 billion years ago, when the universe had expanded to a sufficient size and the average matter density had fallen to a sufficient level that dark energy's contribution to the total energy budget began to dominate. Before that transition, the universe's expansion was decelerating. Gravity, acting on the total matter content, was slowing the expansion that began at the Big Bang. After that transition, the expansion began to accelerate, driven by dark energy's repulsive effect on the geometry of space-time. The cosmic web continued to evolve, but in a modified context. Structure growth slowed because the accelerating expansion made it harder for gravity to draw matter across large distances into increasingly separated concentrations. Voids, by contrast, continued to grow. The accelerating expansion of space added to the evacuation of void interiors driven by gravitational outflow, enlarging the underdense regions at a rate that would not have occurred in a matter-dominated universe without dark energy. In the current epoch, voids are growing both because matter is flowing out of them gravitationally and because the space within them is expanding at the accelerating rate driven by dark energy. These two effects compound each other in void interiors in a way they do not in denser regions, where gravity partially counteracts the expansion. Projected forward in time, not to any specific moment, but across the broad trajectory that the physics implies, the universe becomes increasingly a place of voids. As dark energy continues to drive accelerating expansion, the large-scale structure freezes progressively into place. The great clusters, bound by their own gravity, persist as islands in an expanding sea, but the distances between them grow, and the filaments connecting them thin and eventually become too diffuse to sustain galaxy formation. The voids expand to fill the increasing volume of the universe. The cosmic web, over timescales far longer than the current age of the universe, becomes a collection of isolated gravitational islands separated by ever larger regions of profound emptiness. This is not a speculative extrapolation. It is the straightforward extension of the current cosmological model into the future, given the observed properties of dark energy. If the dark energy is indeed a cosmological constant, constant in its density, undiminishing as space expands. Then the late universe is one in which voids are the dominant feature of the observable cosmos, as they already are by volume in the current epoch. The question is not whether this will happen, but how quickly, and with what observational signatures along the way. Understanding that trajectory, measuring it precisely enough to determine whether dark energy truly is constant, or whether it weakens or strengthens over time, is one of the primary scientific goals of the next generation of large-scale structure surveys. The Dark Energy Spectroscopic Instrument, Euclid, the Vera Rubin Observatory Survey, and the Nancy Grace Roman Space Telescope each address this question through different observational strategies. And each uses void statistics as part of its toolkit. The void population across a wide range of redshifts, spanning several billion years of cosmic history, encodes the growth rate of structure over that period, which in turn encodes the behavior of dark energy throughout those epochs. The future surveys will do more than refine existing measurements. They will extend the characterization of the void population into regimes where current data is sparse, toward higher redshifts, where the universe was younger and the voids less evolved, and toward the extreme end of the size distribution, where the largest and rarest structures live, and where the standard model's predictions are least tightly constrained by existing observation. In doing so, they will test whether the picture assembled from current surveys, the hierarchical void population, the correspondence between observed and simulated void statistics, the relationship between void growth and dark energy, holds at scales and epochs not yet fully explored. The CMB cold spot will be among the features that future surveys address most directly. The angular resolution and sensitivity of coming CMB experiments, combined with deeper and more complete galaxy surveys in the relevant region of the sky, will either confirm the supervoid hypothesis, establishing a coherent physical underdensity large enough to produce the observed temperature decrement through the integrated Sachs-Wolf effect, or constrain it sufficiently to require a different explanation. Either outcome is scientifically valuable. A confirmed supervoid of the required scale would represent one of the largest coherent structures ever identified in the observable universe, and would place specific constraints on the initial power spectrum at large scales. A definitive ruling against the supervoid explanation would push the cold spot back toward the primordial anomaly category, requiring an account of why a fluctuation of that magnitude appears in a CMB map that is otherwise consistent with standard inflationary predictions. The Hubble tension, too, will be tested against the KBC void hypothesis with increasing precision. Surveys that map the three-dimensional density field around our position with sufficient resolution and completeness will determine whether the underdensity is as large and as deep as current evidence suggests, and whether its gravitational dynamics are sufficient to explain the discrepancy between local and CMB-based Hubble constant measurements. If the void explanation proves adequate, it will represent one of the more elegant resolutions of a major cosmological anomaly, not through new physics, but through a more complete accounting of the observer's position within the existing physics. If it proves insufficient, the tension will continue to point toward something genuinely new in the fundamental theory. What all of these open questions share is a common structure. They are questions about the relationship between the universe's large-scale geometry, its distribution of matter and energy across the full observable volume, and specific anomalous features in the data that do not fit comfortably within the current best model. The voids are implicated in each of them, as potential explanations, as sensitive probes, as environments where the physics relevant to the anomaly expresses itself most clearly. The scientific agenda of the next decade or two in observational cosmology is, in significant part, an agenda organized around what the voids can tell us. This is a remarkable position for structures that for most of the history of modern astronomy were treated as the absence of the interesting things, rather than interesting things in themselves. The transition from void as background to void as subject, from the negative space of the cosmic map to one of its most scientifically productive features, is a conceptual shift that has accumulated quietly over 4 decades of observation, simulation, and theoretical development. It has not announced itself with a single dramatic discovery. It has arrived through the gradual accumulation of evidence that the empty regions of the universe are speaking, in a language of underdensity and outflow and dark energy dominance, about the fundamental properties of the cosmos. That language, once learned, changes how the universe looks. The maps of the cosmic web that have become iconic images of modern science, those sweeping visualizations of filaments and nodes on a background of dark emptiness, are typically read for their luminous structures, for the threads and knots of matter that catch the eye. But the empty regions in those maps are not passive background. They are the dominant volume. They are physically active. They are expanding. They are constraining dark energy and testing gravity and shaping the galaxies that formed within them. They are telling us, through careful observation, something about where we are and how the universe around us has evolved. The silence in those maps is not the silence of nothing. It is the silence of a physical environment, coherent, structured, dynamic, that required the development of new tools, new methods, and new conceptual frameworks to make legible. It is the silence that preceded every map that was ever made of it, waiting for the instruments that could read an absence as a signal, and the scientists who recognized that what was not there was as meaningful as what was. Return for a moment to the question that opened this journey. Why should the universe's emptiness feel wrong? Why does a region hundreds of millions of light-years across, containing almost no galaxies, produce a sense of something missing? A feeling that the universe has failed, in that place, to fulfill some expectation. The answer lies in the nature of the expectation itself. We expect the universe to be filled because filling is what structure does in our experience. Rooms fill with objects. Skies fill with stars. Maps fill with named places. An empty region on a map of the familiar world suggests an error, a place the cartographer has not yet reached. Applied to the cosmic map, the same intuition produces the same reading. The voids look like gaps in the survey, places where the data ran out. But they are not gaps. They are the most thoroughly understood regions of the large-scale structure, characterized through multiple independent methods, consistent with each other and with the physics of gravitational evolution from near-uniform initial conditions. They are not errors in the map. They are the map, in the regions where matter chose not to be, or rather, where the physics of the early universe ensured that matter would drain away, leaving these vast domains as the necessary counterpart to every cluster and filament that exists. The universe was never a place uniformly filled with light. From the moment the first density fluctuations were imprinted on the primordial plasma, in the first fractions of a second of cosmic history, at scales and energies beyond any direct observation, the pattern that would eventually become the cosmic web, with its voids and its filaments, was encoded in the initial conditions. The emptiness was always going to be there. It was written into the beginning, seeded by the same quantum processes that seeded everything else, and it has been growing, deepening, and expanding ever since. The voids were not discovered when astronomers first noticed the blank regions in their maps. They were discovered when those blank regions were understood to be something, when the absence was recognized as a structure, the silence as a signal, the emptiness as a form of information about the universe that no amount of studying the bright parts alone could have provided. That recognition took time and instruments, and the development of entirely new ways of thinking about what a map of the universe is supposed to show. What it shows in the end is mostly this: an intricate architecture of matter, traced against a background of profound and structured emptiness, expanding quietly into a future that will be defined by the growth of that emptiness as much as by the persistence of the light.